Here I have a compass sitting next to a wire. Now this wire is connected to a power supply, so that current is actually going to come from the bottom of the platform up through the wire. So current is going to pass up this way. All right. So current will pass up through the wire. Any questions about that? Now right now the compass is pointing which way?
North.
North. Okay. Because of the Earth's magnetic field. If I take this compass and I move it around the wire, okay, it's just turning because I picked it up. Right. If I move it around the wire, it's going to stay pointing in the same north direction. Right? Rex.
No, my goal is to ask why so I understand.
Okay, you're asking why like you're a 3-year-old.
Why?
Okay. Why does it do that? Because the Earth has an inherent magnetic field that the compass aligns with. Okay. We talked about that last week and you knew it. So the fact that you're asking why now just tells me you're trying to make yourself YouTube famous.
It's a refresher.
No, I'm trying to help our viewers.
Okay, thank you, Rex.
That's it.
Our viewers. They're our viewers, huh?
Yeah.
Only I'm getting the commission checks.
We contributed.
All right. Any questions about the magnetic field here? All right. Now, in a moment, I'm going to turn on the power supply. You'll be able to tell when I turn on the power supply because something will happen. No, nothing's exploding. Okay. I think this is really exciting. So you guys probably think it's going to be meh. All right. You guys ready?
I think the needle is gonna point.
I want you to watch the needle on the compass. Okay. Ready? Set. Go.
Oh my
Oh,
god.
that's it? That's all. I thought it was gonna. At least
Nothing happened.
I thought it was at least gonna spin around. Like,
Yeah.
full circle.
Move.
Okay.
I thought it was gonna point towards the core.
A little bit. Okay. Let's go to a different spot then. Let's go right here. Can we all see that compass? Can we see it?
I dare you to touch the
You
wire.
guys ready? Set. Go.
Whoa.
Wow.
That's cooler.
Okay. Move more.
Leaping
Right?
electrons.
Okay.
Dang electrons.
Let's go right here.
Lizards.
So the air conditioning is still broken.
Okay. Ready? Set. Go.
Wow.
So, what is this telling us about the current through the wire? It's creating a what?
Magnetic field.
A magnetic field. Now remember, compasses point in the direction of the magnetic field lines, right? So at this point, the magnetic field lines are pointing this way. They're pointing to the right of the room, right? As I move the compass around, you will notice that the compass needle is pointing in such a way that it makes a what around the wire? Makes a circle around the wire. Ah!
Touch that part.
Coded in.
Touch that part.
So all the way around the wire, there's a magnetic field that's now encircling the wire.
Touch that part.
Okay. If I shut off the current, it goes back to normal.
Crazy.
Does that make sense? Now I'm going to flip the direction of current flowing. Okay. So I'm hooking it up now so that current is flowing down the wire instead of up the wire. Current is now flowing down the wire. Okay.
How do you know that?
Be careful. Because the red is the negative side, and when current flows, electrons come out of the negative side.
Oh.
Okay. You ready? Set. Go. Okay. A little adjustment, right? We go to the other side. Sleep autofocus. Ready? 1, 2, 3. Okay. Go in the opposite direction. So what you might notice is that when I have the current the other way, this needle was pointing almost correct on the top end and towards me on the other end. Well, now the direction is flipped. The reason being is the current is traveling in different directions. The way we figure out a current through, or the magnetic field surrounding a current carrying wire is using another right-hand rule. Okay, so we have a right-hand rule that looks like we're playing cops and robbers, right? We'll call that one right-hand rule number 1. Or was Michael wanted to call it physics gang signs? Or was it Caleb?
That was Locke.
That was Locke wanted to call it physics gang signs? Okay. So, the one that looks like you're playing cops and robbers, that's right-hand rule number 1. Now this one is right-hand rule number 2. The way it works is you take your thumb and you point it in the direction the current is traveling. I know we can't see my thumb. Back this up a little bit. So that way all the YouTube viewers, Rex, can see my thumb and can see you. Okay? So, my thumb is going to go in the direction of the wire. Okay? And I'm going to wrap my fingers around the wire, and that's the direction of the magnetic field. So as the current goes down the wire, the magnetic field goes around it. Or if the current comes up the wire, the magnetic field goes in the other direction. You guys see that?
Yeah.
Yeah? Okay, let's draw some pictures on the board.
Now, why does it do that?
Why does it do that? Great question, Rex. I like your why question now. They're just being redundant. My question. All right. So why does it do that? Remember we talked about electrons are like tiny what?
Oh my god.
Tiny magnets. Okay. Electrons are like tiny magnets. We talked about this. You guys saw us in a video. All right. So as the electrons move, what they do is they create a magnetic field. Okay. Oh, we've gone out of focus. Come on, refocus. That's all I'm trying
I
to
feel like
Come
I'm
on.
gonna throw my yogurt.
Guys, I understand it's warm in here. We just gotta suck it up.
What?
Really, really warm.
Can't.
All right. It's a little warmer than that, Rex. All right. So. Why does that happen? Because current passing through a wire creates a magnetic field. The reason why is we are sending a whole bunch of electrons through the current or through the wire at the same time, which creates a magnetic field because all those electrons act like tiny magnets. Current passing through a wire creates a magnetic field. All right. So, if this is my wire, and I have current going this way, we're going to call that the direction the electrons flow. So we're talking about current here, guys. We're talking about the directions the electrons flow. So the current passing through the wire. The way I figure out the magnetic field surrounding this wire is you take your thumb and you point in the direction of the current. So my thumb goes in the direction of the current, and then I wrap my fingers around the wire. All right? So I wrap my fingers around the wire. So that means underneath the wire, the magnetic field points into the board. That's where my fingers go. On top of the wire, the magnetic field points out of the board. So these are at you. Okay? These are away from you. Okay? So surrounding that wire, we have a magnetic field. Does that make sense? And when I'm saying current, I'm saying the actual flow of electrons. If you've done any study of Ohm's law, you know that traditional or conventional current flows the opposite direction. We're talking about actual current here, the actual flow of electrons. So what happens if I have the current going the other way? X's are on top. Perfect. Okay, current's going the other way, so X's are on top, dots are on bottom, right? Away from us on top, toward the sun bottom. So now what we've created with current passing through this wire is a, let me know? What we've created with current passing through this wire, we've created a magnetic field. Boom! Okay. It's not quite an electromagnet, Caleb, but when I start to coil these wires together and get a bunch of magnetic field lines pulling the same way through material, that's how I make electromagnet.
Is that what that is?
Well, this is a coil wire. This is not an electromagnet because it needs something inside of it. It needs a piece of metal to align all its electrons.
You should put a piece of metal.
Okay. Not today. Why? Maybe tomorrow. Okay. All right. Any questions? So now what happens with these induced magnetic fields? Do you think these magnetic fields will attract each other or repel each other? Okay. Why do you say repel, Jose? Because the X's, right? This means if this is the north side of the magnet, then what's this?
The north side.
The north side, right? Do norths attract or repel? Repel. So these wires would actually push each other apart. Okay? If I wanted these wires to attract each other, what would I have to do to the current through this one?
Put it the same way.
Flip it around. Okay? So we can create wires that will attract or repel each other. I would have shown you guys, but it gets kind of windy in here. And last time I tried the experiment, everybody's like, "Oh, the wind just blew it." Like half an hour of me making sure this experiment was working, and then everybody just says, "Oh, it's just the wind." Okay, we'll go with that then. All right. Any questions about the magnetic field surrounding these wires? Right. So it's like we have a field line that goes out of the bottom into the top, and then behind, like that. Okay. This one kind of comes. We'll go into the top. Oh, I drew that backwards. Add us here. Sorry. So it looks like that. So out of the top into the bottom. This one goes into the top and out of the bottom.
What goes out of the...
Any questions? So now here's a straight on view of the wire. This dot means the current is coming which way?
That way.
Towards you or away from you?
Towards you.
Towards you. This means the current's coming towards you, right? So if current's coming towards me, I curl my fingers around the wire, it tells me that my magnetic field is clockwise or counterclockwise? Counterclockwise. So this is the magnetic field. Does that make sense? And this other one, current is pointing into the board. My magnetic field is clockwise. So magnetic field is clockwise because the current is going opposite directions. Okay. So right here we kind of have two north sides of magnets that will repel. All right, Michael, you okay? Yeah? Yeah. Skylar, you all right? All right, now, here's the question. What would happen if I were to take a compass and set it right here? Which way would the compass needle point? So I'm going to draw a green box right here. The green box is going to represent a compass. Which way will that compass needle point? Right, left, up, down, towards, away. Which way is it going to point? Nope.
Right.
Nope.
Away.
Okay, remember, compasses points in the direction of the magnetic field line at that location, right?
Oh.
So which way does the magnetic field point here?
Left.
Down.
Come on, away.
Towards you, right? So magnetic field is pointing towards me. That's what the dots mean, right? So the compass would point towards me on top of this wire. Which way would the compass point below it?
Away.
Away. Which way would the compass point if I was in front of the wire?
Spin everywhere. Down.
Out of the board, into the board.
Wait, which one are we doing?
This one, the compass in front.
Down.
It's going to point down. So this compass would point down. Does that make sense?
Yeah.
Yeah.
So does this happen to all wires that have
Yep.
electricity running through them?
Yep. So the wires in your cell phone that have small little amps going, small currents going through them, they are creating magnetic fields. Okay. And actually, if you bring a magnet close enough to any piece of electronics, then the moving magnetic field can disrupt the current through the wires. It won't be a constant disruption, but it'll be it can be a disruption enough sometimes to actually break the
So that's
electronics
why,
through
like,
ice.
when you used to put magnets by a TV, it'd go all wonky.
Yep.
Can we do that with that TV?
No, it's not plugged in, or the outlet doesn't work.
Why are you pointing at me?
Okay.
Are they
So-
ever gonna fix that?
It was a group
By the
effort.
summer. All right. So right here, this is another compass. Which way is the magnetic field point? Away. Which way is this magnetic field point? Towards. And which way does this one point?
Up.
Up. So we're kind of creating that circle. Does that make sense? A compass on the back of this wire is going to point, on the back of the top wire is going to point
Up.
Up. A compass on the back of this bottom wire will point
Down.
down. So I'm making that complete circle. All right. Or we can do the same thing over here. If I put a compass at these 4 locations, right? This is kind of like what I showed you in the demo. Okay. When the current's coming at you at all 4 of those locations, my fingers point the direction of the magnetic field, right? So my fingers point the direction the compass will point. Because that's the way the magnetic field's going. Drawing the same compasses on this one, what can you guys tell me about the arrows? They will point how? Good. Opposite of the top one. because the current's going a different way, which means the magnetic field goes a different way. Any questions? So these currents to these wires are creating magnetic fields, right? Right?
Yep.
And those magnetic fields will then cause that wire, if it were in a magnetic field, to feel what?
Force.
A force. Okay? So going back to, George, going back to an example or a demo we did at the beginning of this unit, you guys thought it was all so exciting because nothing exploded, right? Nothing got blown up. All right? Here I have a horseshoe magnet, right? Currents passing through this wire as it goes through the horseshoe magnet. Do you guys remember what happened?
It moved a little bit.
It moved, right? I wouldn't call it a little bit. I'd say it moved a lot. Okay? So, use the right-hand rule with this wire to try to figure out which way it moved. The current is the direction of electrons flowing. Okay, so take a moment or two while I draw some better horseshoe magnets than I had earlier. Okay, so which way is this wire going to move? Which way is that wire going to move?
Up.
Up. Why up?
Because
Okay. Pointer finger is the velocity, right? Current's going that way, that's my velocity. B field is kind of into the board. I know it's got a little perspective to it, but B field's into the board, right? So thumb is up. So the force felt by this wire will be up. Okay. Does that make sense? If I flip the current around, which I did in the experiment, what would happen?
you would do crazy stuff.
The force would be down. If I flip the magnet around, so I took this magnet right here, and I flipped the magnet around, what would happen to the force? It'd be down. Okay? Any questions? Oh, we made a mistake, guys. That force isn't up because these are electrons. What do I do with my right-hand rule? You gotta flip it, so this force should be down.
Frank, your videos are too confusing for people.
Okay. Any questions? Any questions? So why does that wire feel a force?
That's what I was just gonna ask.
Because within that wire there's moving what? Electrons. Electrons feel a force as they follow this equation. Right? F equals QVB. Where F is the force, V is velocity, B is the B field, right? And all of these have to be perpendicular. They're not perpendicular, no force. So if I ran my wire from north to south, it wouldn't move at all. Captain, put my bar magnets down, please. Thank you, sirs. Almost said that on top of the iPad. That'd be bad. All right. So any questions about this equation? We've seen it before, right? Okay. Now I'm going to do something called dimensional analysis, okay, or unit analysis. So what I'm going to do is I'm going to plug in the units for Q, V, and B. What's the unit for Q? Coulombs, right? What's the unit for velocity? Meters per second.
Coulomb.
What's the unit for B field?
Coulomb.
Good, Tesla. Throwing enough letters at us here. All right. So magnetic field is Tesla. Velocity is meters per second. Coulombs is, or charge is coulombs. Really, just like country music. CMT. Come on now. All right. Now, the way division works is that this is all multiplication. I'm dividing everything by S, aren't I? Right? So I can rewrite this as C over S MT. Remember, T was what? Tesla. Now, if I just have M by itself, that's meters, right? What's a meter? Distance or a... Caleb, what'd you say?
I was going to say a lot of centimeters.
Okay. A length. Right? Distance, radius, they're all lengths. Aren't they? So we have Tesla was B field, meters is length, right? What's C over S? Charge per second. Anybody know? Like a velocity, it's like a charge velocity.
What is
The big I. What does big I stand for? Nope. You're hoping. I stands for current. We've all heard of current before, right? And get this, its units are amps. Because the guy who studied current, his name was Ampere.
So 3 different letters.
Yeah, 3 letters for one thing. Alright, so current is I. L is the length. The length of what?
The field
Not the length of the field, the length of the...
force.
We're getting there.
Magnetic.
What is it, Non? The wire.
Why?
Because the wire carries the charge, right? The only time the charges will feel a force is when they're within the magnetic field. So that L is the length of the wire within the magnetic field. So length of the wire within the B field. Okay. B is still magnetic field. And F is force. What in this length has to be in? Meters, good. And B field is still in Teslas, and force is still in Newtons. Any questions? So that's why the wire that had the current passing through it, that's why it felt a force when it was within the magnet, the magnetic field. All right? You guys remember watching this demo?
Nope.
Okay. Where did it look like the wire was pulled from or pushed from? Was it from the sides or was it from the middle?
Middle.
Middle. Okay. This popped up in the middle or pushed down in the middle because that's where it felt the force. All right. Let's look at these 2 drawings real quick, and then we'll move on to some examples. All right, Skylar. Skylar. Someone get Skylar awake. I know it's hot, buddy. We gotta stay awake. Okay, too long a weekend. All right, so here's our horseshoe magnet. North, south. Which way is the magnetic field point? Left or right? Katrina, left or right?
Yeah,
To the right. Good. You should try to sleep during your test. State-specific testing. It'll be the same state you learned it in. All right. So north to south. That's the way the B field points, right? Which way does this one feel a force? So I'm guessing a lot of you are gonna start going. Mr. Branch just taught us this rule today, so we're gonna use this one. No, we don't use this one. This rule, the right-hand rule, where I just curl my fingers, that's only for determining magnetic fields around a wire. Just because this is a wire, to figure out the force felt, we still use the Cops and Roberts rule. Okay. So B field points this way. Velocity is towards us. Which way is the force? Up. So this one will feel a force up. If these were protons, but they are
electrons.
So the force is down. I almost made the same mistake twice. Means I didn't learn anything. Yeah. So force is down, right? Does that make sense?
We should be teaching you.
You should be. So then I can ask you why. So B field still points left to right in this one. Velocity is now into the board, right? My current's in the board, velocity is into the board. B field is right. The force is down if these were positive, but they are negative, so the force is up. So we basically recapped an experiment that we did at the beginning of this unit. Any questions? No, we're not done. Guys, this is the most exciting part of my day, teaching you physics. And you won't always want to cut it short.
You got burnt out. Then you must have a very bland life.
Well, I should say this is the most exciting part of my work day. Because going home watching Sophia the First with my daughters, that's a good time too. Going outside and pushing them in the big Lil-Tex trucks and smashing each other, that's a good time as well. Alright, so here we go. Example 31 and 32. Once we're done with these examples, then we'll be done, Katrina. How's that sound?
Yeah, these are going to take like 30 minutes.
No, they won't. Okay, so example 31. A magnetic field encloses a 4 centimeter piece of wire and exerts a 3 Newton force. Downward on the wire as 2 amps of current passes through the wire from right to left. What is the magnetic field? What is the magnitude and direction of the magnetic field? So it says the current. See, current passes through the current from left to right. So our electrons are going that way. right? Which way do they feel the force? Nope. They create a magnetic field that goes that way, Omar. But which way do they feel the force? What does it say in the problem? Downward. So there's a downward force acting on this wire, right? Which way is the B field?
Right.
Which way is the B field? Towards us or away from us? Okay. If these were positive charged, it would be
Down.
towards us, right? But since they're negative charged, the B field is away.
Okay, if the force is down, can't you just spin it anyway?
Huh?
If the force is down,
But you gotta keep your velocity in the same direction.
what direction of what?
Okay, velocity goes left to right.
Oh, okay.
Okay, so my force is down. So as I flip it, I still gotta keep my velocity going the same direction. Okay, all you're doing is you're changing the direction of your last vector. All right. So since it's negative, I'm changing the direction of my middle finger, the opposite way. Okay, I can't pick up or down. I gotta pick. Since it's going towards you, I gotta pick away. All right, good question. So let's figure out that force. Oh, so force is 3 newtons. Current is 2 amps. L is 4 centimeters. Can I keep it as 4 centimeters? No, it's gotta be 4 times 10 to the negative 2 meters. Okay. Any questions? Guys, any questions? Yeah. So, in order to find the B field, we need to use this equation: F equals ILB. Okay. So F equals ILB. So F is 3, I is 2, L is 4 times 10 to the negative second, and B we need to solve for. Now, while you guys are solving, I want you to think about something. What has to be the relationship between force, current, and B field? Don't shout it out. Think for a second. No, I already shot it. Well, now what was it? Perpendicular. Good. We look at our picture. Our current, our force, and our B field are perpendicular, just like it was with QVB.
So is it perpendicular that you can use it?
What? They're not perpendicular. This equation won't work. So if the wire was traveling parallel to the B field, it wouldn't feel the force. All right. All right. So what happens? Divide, right? What do we get? What's our B field? 37.5 equals B. That's Tesla's. Any questions?
That's a lot.
You guys, any questions?
Wait, you're still recording?
No, I'm just being inappropriate.
Alright, I would like you guys to try example 32. Well, good, I can watch the video then write her up.
That was a good one.
Alright, try example 32 real quick.
It's reproduction system.
What?
Reproduction system.
Oh, goodness. Try example 32. Kyle, wake up. Kyle, wake up. Yes, I'm still recording.
Feline.
I'm not lying.
Wake up, sir.
It's like Hawaiian.
There's a fly.
Okay. Okay. Hi.
Oh.
That's a big fly.
What did he do? Eat you?
Yeah.
Well, you already smart.
Can you fill my water bottle? I want cold water.
Global 12 wire. Wow.
That's so gross.
Hi.
Guys, the MT is millitesla. So it's 4 times 10 to the
Whatever.
negative third. Good.
Why?
That'd be micro, close. Or not micro. That don't even be micro.
Are you serious?
Micro's negative 9.
Do
No,
you
negative
know
6. Micro's negative 6. Pico's negative 9.
I hit it too.
Regular Cheetos are disgusting. Yeah.
I hit corn.
Aw. It's good. It's better than hot Cheetos.
Oh, those are yours?
Kyle, how about you do the example since you wanted to sleep earlier?
I gotta eat.
Oh my goodness. Hey, be sure to rub your eyes if you need to.
Wow.
It'll make you cry.
Hot sheet on the
Come on, Kyle, let's go.
I'm done with it already.
You done with it? Let me see your answer then. What's your answer for 32? Yeah? Aha, you got a 0 on it. Nice job. Guys, since you wanted a traditional test, you need to know how to do this on your own.
I'm gonna feel so bad that correctors aren't gonna do anything for me, so I might as well do the take-home test.
Yeah, can we do the second one?
Nope.
I did finish.
The trainer. Wow. Is it 2 times 4 times 500?
No, the 4 has to be converted to normal test list. Guys, too loud.
Too loud.
Wait. Can't swear.
No, swear. Okay, that's that.
Yep. So, a 2-meter section of power line is subject to a 4 microtesla magnetic field from current passing through a nearby power line. What is the force felt by this 2-meter power line when a 500 amps of current passes through it? Alright, so, let's figure this out. Now, one downfall of this example is the current as it goes through power line is alternating direction. It doesn't always go the same way. So, sometimes they align where they make attractive forces between the wires. Sometimes they align when they make repulsive forces. Alright, so the force, F equals ILB, right? So 500 times 2 times 4 times 10 to the negative third. Right? What do we get? 4. Good. The force is 4 newtons. I'll come up in a second, Jose. Any other questions? No. No.